Right now, while you are hearing these words, a phone on a desk in Pasadena is not ringing. It does not need to. The person waiting for it already knows the answer is still hours away, crossing more distance than any human voice has ever crossed. Two machines built before most of today's engineers were born are still moving through space no model correctly predicted, no probe has ever followed, and no replacement is being built to take their place. They do not know they are old. They do not know that the people who built them are gone or going. But the people still answering their calls are running out of time faster than the machines are. This is the story of Voyager 1 and Voyager 2, the two spacecraft that left Earth in the late summer of 1977 and simply never stopped. You already know some version of that story, the golden record, the grand tour of the outer planets, the improbable decades of survival against odds nobody in 1977 would have taken seriously. This channel breaks down real space discoveries without the exaggeration, and the discovery worth telling honestly this time is not sitting in the data. It is sitting in the building where the data lands. If you are old enough to remember either launch on the news, you have already personally outlived most of the assumptions anyone made at the time about how long these machines would keep working. Somewhere in Pasadena, a small and shrinking group of engineers, several of them closer to retirement than to their first day on the job, are the entire reason either spacecraft still has anyone to talk to. Voyager 2 left Kennedy Space Center first on August 20th, 1977. Voyager 1 followed 16 days later on September 5th, launched onto a shorter, faster path that let it overtake its twin before either had left the solar system behind. Voyager 2 flew past Jupiter in July of 1979, then Saturn 2 years after that, then became the only spacecraft in history to fly past Uranus in January of 1986 and Neptune in August of 1989. Voyager 1 reached Jupiter in March of 1979 and Saturn in November of 1980. Then turned sharply out of the flat plane the planets orbit in, trading any chance at the ice giants for the fastest possible road toward interstellar space. The official mission plan called for 4 years of flight. In 1990, with both spacecraft still healthy and both already well past their original planets, NASA quietly renamed the whole effort the Voyager Interstellar Mission, a dry piece of paperwork that amounted to an admission that this was no longer the mission anyone had originally signed up for. We are now closer to 50 years than 4. You do not need to remember the exact dates to feel the shape of it. Two machines launched 16 days apart, still following two different roads out of the same solar system. Here is the part almost nobody covers when they tell this story. A spacecraft does not fly itself, not even one running largely on autopilot across billions of miles of empty space. Every command it executes was written by a person, checked by a person, and transmitted by a person who then waited, sometimes the better part of 2 days, simply to learn whether it had worked. You will not find a precise current headcount for the flight team in any NASA press release, and this script is not going to invent one either. What can be said honestly, because the agency's own engineers have said versions of it themselves, is that the team is small enough that a single retirement can change what the mission is willing to attempt next. Two of the people this story can name with real confidence are Suzanne Dodd and Edward Stone. Only one of them is still alive to hear how it turns out. Suzanne Dodd first touched this mission in 1984. As a young sequence design engineer working on Voyager 2's approach to Uranus. Sequence design meant writing out, in advance and in exact order, every instruction the spacecraft would carry out during a flyby that would be over in a matter of hours. There was no going back. Once the sequence began running on its own, more than 1 billion miles from anyone who could step in, it simply ran, for better or worse. By 1989, 5 years later, she had helped design the exact command sequence for Voyager 2's closest approach to Neptune, the last New World either spacecraft would ever visit. Then she left. She worked the failed Mars Observer mission. She led a team of roughly 40 people on Cassini at Saturn. She ran the Spitzer Space Telescope program for years, then NuSTAR after that. By any normal measure, her career had moved on completely. But in 2010, Suzanne Dodd came back as the 10th person to hold the title of Voyager Project Manager, and the person still holding it today. She has since described the two spacecraft in blunt engineering language that reads less like a status update and more like a warning. Everything on board, she has said, is single string. There is no backup system quietly waiting behind the one currently doing the work. If a single part fails for good, there is no second part to switch to. Today, she also directs JPL's entire Interplanetary Network Directorate, the division that runs the Deep Space Network itself, which means the same person now oversees both the spacecraft and the ground antennas that make listening to it possible at all. You can draw a straight line from the young engineer sequencing a Neptune flyby in 1989 to the project manager, still making difficult calls about a dying spacecraft today, and it is the same person. Running a 50-year-old spacecraft this way, with no second system standing behind the first, is either the bravest possible approach or the most reckless one. Honestly, it is probably both at once. This is roughly what the job still looks like decades later for whoever is doing it today. You write an instruction, you check it, then you check it again. Because there is no version of this where you get to send a quick correction 5 minutes later. You transmit it toward a target that is not actually where it appears to be. Because even light needs real time to cross real distance, then you wait. For Voyager 1 right now, that wait runs to more than a full day each way. The better part of 2 full days there and back before you find out whether the machine understood you at all. Edward Stone is the reason there was ever a mission for Suzanne Dodd to come back to. He became Voyager's project scientist in 1972, 5 years before either spacecraft launched, and he held that position without interruption for 50 years, overseeing roughly 11 separate science teams made up of around 200 researchers in total. He once described his own job as an impedance matching function between what the engineers needed and what the scientists wanted. A fairly dry way of putting it. For 5 decades, he was the final word on where the cameras pointed, and on which instrument got power when there was not enough power for all of them. He also said, more simply, that becoming Voyager's project scientist was the best decision he made in his entire life. For a full decade in the middle of all that, from 1991 to 2001, he was not only Voyager's scientist, he was the 7th director of the entire Jet Propulsion Laboratory, responsible for every mission the lab ran, not just the 2 oldest ones. He kept the Voyager title through all of it anyway. He received the National Medal of Science in 1991 and the Shaw Prize in Astronomy in 2019, and he still chose, every single year in between, to keep showing up for the mission he had started when Richard Nixon was president. Sit with what 50 years actually means for one person attached to one mission. His own daughters were born, grew up, married, and had children of their own while he held that job, and Voyager, in his own words, just kept going. He finally stepped back from the role in 2022, 50 years almost to the day after he first took it on. He died on June 9th, 2024, in Pasadena, at 88 years old, in the same city where the mission he ran for half a century is still, right now, listening for a signal that takes the better part of 2 days to return. He did not live to hear it go quiet. He almost certainly never expected to have to. The harder problem cannot be solved with a new hire. Both spacecraft still run on flight software written in the 1970s, on computers holding a tiny fraction of the working memory of an ordinary kitchen appliance, using programming conventions that most computer science departments stopped teaching a generation ago. NASA has not published an exact figure for how much of the original design documentation survives only on paper in filing cabinets, rather than in any searchable database. This script will not guess. It will describe the problem honestly instead of inventing a number that only sounds precise. Imagine being handed a program you cannot fully read, written in a dialect you were never taught in school by someone who retires in a year. What is fair to say, because JPL's own engineers have said versions of it publicly, is that real fluency in this particular spacecraft cannot simply be hired in from outside. It has to be handed down in person, one engineer nearing the end of a career teaching one engineer near the start of theirs, inside the same building, before the knowledge runs out on its own schedule. Nobody planned it this way on purpose. It happened gradually, one still working system at a time, until the whole arrangement quietly became irreplaceable, without anyone ever formally deciding that it should be. The ground side of this story is aging too, which almost nobody mentions in the same breath as the spacecraft. Every command reaches Voyager 1 or Voyager 2 through one of 3 Deep Space Network complexes in Goldstone, California, Madrid, Spain, and Canberra, Australia. Each one centers on a 70-meter dish. Every one of those dishes has been listening to deep space since before most of today's engineers were born. You have likely never seen one of these dishes in person, and neither have most of the scientists who depend on them every day. NASA itself has called those dishes aging and increasingly difficult to maintain. Rather than replace them, the agency chose in 2021 to rebuild all 3 from the inside out, betting that a decades-old design, carefully refurbished, still had decades of listening left in it. It is the same bet the flight team makes about the spacecraft, and in a quieter way, the same bet the spacecraft has been making about the people for almost 50 years now. Voyager 1 crossed into interstellar space first, on August 25, 2012, at a distance from the Sun of about 121 times the distance between Earth and the Sun. Proving it took the better part of another year. By then, Voyager, one's own plasma instrument, the one built to directly measure the density of charged particles around it, had already stopped working properly, degraded years earlier by simple wear. So scientists were left waiting for something rarer than a working sensor. In March of 2012, the Sun itself threw an unusually large outburst of charged particles outward. More than a year later, in April of 2013, that outburst finally reached Voyager 1 and set the plasma around it ringing, almost like striking a bell nobody could see, only hear. You can think of it as scientists waiting for the universe itself to ring a bell they had no other way of hearing. From the pitch of that ringing, they could finally calculate the density of the material surrounding the spacecraft precisely enough to say, with confidence, that Voyager 1 really had left the sun's bubble behind. NASA did not confirm the crossing publicly until September 12, 2013, more than a year after it had actually happened, because that is how long it took to be certain rather than merely hopeful. Voyager 2 had an easier time of it. Its own plasma instrument was still working when it reached the same boundary on November 5, 2018, at a distance of roughly 119 times the distance between Earth and the Sun. This time, scientists did not need to wait for the Sun to help them. They could simply read the answer directly, in real time. Edward Stone, then in his early 80s and still the mission's project scientist, announced Voyager 2's crossing that December himself, more than 4 decades after he had first taken the job. Here is the twist inside all of that. The same instruments that helped prove those crossings are now among the very ones being switched off to save what power is left. But before we get to what has been lost, here is what almost broke completely, twice, within months of each other in 2023. On November 14th, 2023, Voyager 1 started transmitting gibberish. Not silence, something stranger than silence. The spacecraft kept sending a clean, strong radio signal right on schedule, but the information riding on that signal had turned into a repeating pattern that meant nothing to anyone reading it on Earth. For weeks, the team did not know whether the spacecraft itself was dying or only its voice was. Every diagnostic they wanted to run had to be written, transmitted, and then left completely alone for the better part of 2 days before any answer could possibly return, because that is how long light itself takes to cross the distance involved. If you have ever sent a message and had to wait 2 full days just to learn whether it arrived, you already understand roughly what that month felt like for the people running this recovery. By December 12th, engineers at NASA's Jet Propulsion Laboratory had traced the fault to one failed section of memory inside the spacecraft's flight computer. One tiny piece, gone. It had worn out after decades of continuous operation inside one of the harshest radiation environments any human-made object has ever been asked to survive. Roughly 3% of that memory bank was gone for good. Nobody could fly out and replace it, not at this distance, not ever. So the team rewrote the spacecraft's own instructions to route around the damaged part of itself. They broke that replacement code into pieces small enough to fit inside whatever working memory Voyager 1 had left to spare, and sent it out across billions of miles, one careful piece at a time. There was no way to know if it had worked, not until the reply eventually came back. On April 20th, 2024, 5 months after it first went quiet in the way that actually mattered, Voyager 1 spoke clearly again. Voyager 2 had its own emergency the same year, for an entirely different reason. On July 21st, 2023, a routine set of commands sent from Earth contained a small error, and Voyager 2's main antenna tilted 2 degrees away from the direction of home. 2 degrees sounds like almost nothing. Across a distance of more than 12 billion miles, it was everything. The spacecraft's signal vanished completely. For the flight team, that particular kind of silence carried a specific, cold meaning, because losing an antenna's aim is usually only caused by one of a short list of very bad things. There was a built-in safeguard, a command that would make the spacecraft realign itself automatically, but it was not due to trigger until October. The team did not want to wait that long to find out if it still worked. On August 4th, engineers at the Deep Space Network's Canberra station in Australia sent what NASA itself has publicly called, in its own plain language, a shout. Just that. One enormous burst of power aimed at a spacecraft that might not even have been pointed in the right direction to hear it. You do not get a second try with a command like that, not at this distance, so the team only got to send it once. Voyager 2 heard it anyway. The antenna turned back toward Earth, and the signal returned, weeks ahead of the automatic fallback the team had built in as insurance in case the shout failed. Both machines survived 2023. Neither survived it for free. And it is worth saying plainly that leaving this much of the mission's safety net resting on a handful of specific human beings, rather than on any documented, repeatable process, was always a risk. It is a risk NASA has known about for years and has never fully solved, because nobody who approved a 4-year mission in the 1970s seriously planned for a 5-decade one. Both spacecraft run on the heat of decaying plutonium, converted into a trickle of electricity that has been shrinking, by design, since the day each one launched. There is no refueling this kind of machine, ever, at any distance, so the team's job for years now has not really been discovery. It has been rationing. You're watching across these dates a machine's senses being switched off one at a time, in an order somebody had to choose. Voyager 1's cosmic ray subsystem, the same instrument whose readings helped prove the spacecraft had actually left the sun's influence back in 2012, was switched off on February 25th, 2025 to save power for whatever remained. Its low-energy, charged particle instrument, which measured the ions and electrons moving through the space around it, followed on April 17, 2026. Only 2 instruments on Voyager 1 are still gathering data today, a magnetometer and a plasma wave detector, and even those are living on a shrinking allowance. Voyager 2 has been drawing on a reserve of backup power meant for its safety systems since April of 2023, an emergency measure that was never supposed to become the normal way of doing business. Its plasma science instrument, the very one that gave Voyager 2 the easier, more direct heliopause crossing in 2018, went dark on October 1st, 2024. Its own low-energy charged particle instrument followed on March 24th, 2025. Every one of those shutdowns was a choice made by a specific person, in a specific room, on a specific day, weighing which piece of a nearly 50-year-old machine's remaining voice was worth keeping, and which one had to go quiet first. No training manual written in the 1970s ever covered a decision like that because nobody writing those manuals seriously believed there would still be a spacecraft left to ration this far out. Even staying pointed at Earth has gotten harder. Small thrusters make constant tiny corrections that keep each spacecraft's antenna aimed precisely at a planet it left decades ago. That job never really stops. Over enough time, residue builds up inside the fuel lines that fire those thrusters. The way any engine gets dirtier, the longer it runs without a service. By late summer of 2024, one full set of Voyager 1's thrusters had grown clogged enough to worry the team. In September, engineers performed what they simply called a thruster swap, switching the spacecraft over to a backup set that had not fired since 2018, betting that years of rest had left it cleaner than the set currently in use. It worked, but there was no third set waiting behind that one. Whatever clogs next on either spacecraft will have to be solved with whatever is left, because nothing further is coming from Earth to replace it. Take a breath there, because that sentence is the whole story in miniature. Somebody sits in a meeting and decides which sense a nearly 50-year-old machine will lose next, the way a family might decide, gently, what an elderly relative no longer needs to be told. In 2022, a documentary called It's Quieter in the Twilight followed some of these same engineers through exactly that kind of decision, week after week, inside a building most of the public will never see the inside of. It did not draw the crowds the launches once did. It is worth finding anyway because it may be the closest thing that exists to an honest record of what this job looks like from inside the building, made while there was still time to make it. If you grew up watching these 2 spacecraft launch, or if someone in your own family built the hardware that made missions like this possible, this is, in a real sense, still your story too. The people finishing it are not so different from the people who started it. Here's the part that is easy to say and hard to actually picture. Somewhere between 2027 and the middle of the 2030s, both spacecraft will run out of enough power to operate even one working instrument. They will not stop moving. They will not stop existing. They will simply go quiet, one final circuit failing after another, while still carrying outward, forever, the same golden record and the same greetings in dozens of languages that they carried out of Kennedy Space Center in 1977. By around 2036, even their faint carrier signal, the bare radio hum that needs no working instrument at all to produce, will likely fall below what the Deep Space Network's aging dishes can still detect. After that, both machines keep flying, without an audience, for longer than anything with a name currently keeps any physical shape at all on Earth. But the people keeping watch will be gone long before that point arrives. Suzanne Dodd will eventually retire. Whoever trains under her will retire after that, and after them, someone else. Whoever eventually watches the very last piece of data arrive will almost certainly never have met Edward Stone, and may not even have been alive when Suzanne Dodd first sat down at a console in 1984. The chain of people will have run out by then to someone who only ever knew this mission as something already impossibly old. Somewhere down that line, for the first time since 1977, there will be a day when nobody left alive remembers how to speak this particular machine's language, even though the machine, technically, might still be capable of listening. Neither spacecraft is aimed at any particular star, but in roughly 42,000 years, Voyager 2 will happen to drift within about 1 7/10 light years of a small star called Ross 248, closer to another sun than either spacecraft has been since it left our own. Nobody will be listening for it by then. It will pass that star anyway, silently, carrying its golden record and its dead languages and its clogged single-string thrusters, because nothing in deep space is there to stop it, and nothing ever was. Go back to that phone on the desk in Pasadena that is not ringing. It was never really about the phone. It was about the fact that somebody is still choosing to sit near it, year after year, for a machine that will keep going long after the choosing stops. This is not really only a story about Voyager. It is a story about what it costs, in ordinary human years, to keep an old and important thing running past the point anyone reasonably expected it to last, and about the people who quietly decide that cost is worth paying anyway. You have just spent real time with two of the oldest working machines humanity has ever built, and with a handful of people still willing to answer when they call. If a story about the people behind the hardware, and not only the hardware itself, is what you want more of from this channel, subscribing is the simplest way to see the next one first. There is a related question worth sitting with, one this channel intends to answer properly in its own episode, rather than rush through here, about what actually happens to a listening machine once the last person who can speak its language finally retires. That kind of quiet, unglamorous devotion rarely earns its own headline, but it is the actual reason any of the rest of this story was ever possible. Thank you for spending this much time on two old spacecraft, and on the small number of people still willing to show up for them.